We are going to discuss the tricks of setting carbocation in correct order of stability. I have observed many students face great difficulty when they face a huge number of carbocations to arrange them in correct order of increasing or decreasing stability. Therefore, it is important to understand the factor responsible for the stability of carbocations. Here you can see we have two similar molecules. Those are carbonyl esters. In example A, we have primary carbocation, whereas in example B, we have secondary carbocation. If you ignore all the stabilizing factor of carbocation stability, then you can wrongly conclude that the second molecule B with secondary carbocation can be more stable as compared to molecule A, where we have primary carbocation. It is not all about primary and secondary carbocation. Yes, primary carbocations are less stable as compared to secondary carbocation when there are no other carbocation stabilizing or destabilizing factor. But if there are some other carbocation stabilizing or destabilizing factor, we need to consider them as well. It is very clear in this example is in case of B, we have a carbonyl group next to further away from the carbocation. You see, this is the carbonyl group with the attached ester functionality in the form of ester, which has no influence on primary carbocation. It means the primary carbocation is independent of neighboring ester functionality, which is electron withdrawing in nature. But in second case, we have secondary carbocation, but there is attached with carbonyl group, which is electron withdrawing in nature. Therefore, the electron density of this secondary carbocation is decreasing. So any substituent, any factor that withdraw electron density from carbocation further destabilize the carbocation. Therefore, a molecule A, even being primary carbocation, is more stable as compared to molecule B, which is although secondary carbocation, but electron withdrawing effect of attached carbonyl destabilize the carbocations. Now let's observe the series of a number of different carbocations. It is clear that the carbocation stability is increasing from left to right. The phenyl carbocation is least stable as compared to secondary allylic carbocation. Why secondary allylic carbocation is more stable? The secondary carbocation, allylic carbocation is more stable due to two factors. One is attached methyl group, which is inductively electron donating in nature and participate in hyperconjugation. There is no bond resonance. Second is the pi electron participation through resonance. The resonating structure support the conjugation of pi electrons, support the carbocation stability in secondary allylic carbocation. In case of primary allylic carbocation, the stability is lesser than secondary allylic carbocation due to absence of the attached methyl group in primary allylic carbocation. Then comes tertiary carbocation, again crowding plus electronic factor stabilize tertiary carbocation. Secondary carbocation, a little less stability compared to tertiary due to absence of one alkyl substituent. In primary carbocation, we have only one alkyl substituent, whereas remaining two substituents are missing as compared to tertiary carbocation. Therefore, primary carbocation is least in this group. Then next comes methyl carbocation, where there is no stability factor, as you can see, neither any electronic nor any steric factors. But even then, there is another example of carbocation. There is secondary vinyl. As you know, I always explain the vinyl group that the CH2, that is methylene, attached to another CH2 is called ethene gas. This is ethene. This ethene group, when connect further to another carbon, then it appears like this, and this functionality is known as vinyl. So we have vinyl group that is attached with methyl. So it is secondary vinyl. As you know, any carbocation attached with further two carbon atoms must be termed as secondary. So this is vinyl and secondary vinyl carbocation. There is no any stability factor other than methyl group, which is electron donating. Whereas the hybridization of carbon, here we have sp2, sp2, sp2. In all these cases, from secondary vinyl to methyl, we have carbocation with sp2 hybridization. sp2 hybridization. But in secondary vinyl, we have carbocation with sp hybridization. You know, in sp hybridized carbocation, the S character is greater as compared to sp2. Here the S character is 50%, where here in sp2 hybridization we have S character around 33.3. So the increasing S character destabilizes the carbocation rather than supporting the stability of carbocation. So the secondary vinyl cation is even less stable as compared to simple methyl due to destabilizing factor. Okay, then we have primary vinyl group, where even there is no methyl to assist the carbocation stability, whereas the carbon bearing positive charge is sp hybridized. Therefore, compared to secondary vinyl, we have primary vinyl carbocation even less stable. In the end, we have phenyl carbocation, which is part of cyclic structure. You know, cyclic structure must have certain requirement to adopt the proper geometry. So therefore, this sp hybridized carbon cannot accommodate itself very well within sp hybridization of carbocation. Therefore, the carbocation with sp hybridization in cyclic structure is the least stable among the non-carbocations. So, you know, these are different carbocations. You have compared all of them with their stability factors, considering their stability factors. In summary, there are three major factors which determine the stability of carbocation. Number one, electronic factor means substitution. If the carbocation is more substituted with other carbons, then this factor will favor the stability of carbocation. Another is electronic factor, that is the neighboring pi electrons in conjugation to carbocation can stabilize the carbocation, as in case of allylic carbocation, or you can say benzylic carbocation. You can mention benzylic carbocation here. This benzylic carbocation, CH2, there is methylene with positive charge to indicate carbocation. This is benzylic carbocation. This benzylic carbocation is primary carbocation but more stable than simple secondary carbocation. This secondary carbocation. This is secondary, this is primary, but due to electronic factors or pi electron in resonance with positive charge, the stability of this carbocation, even being primary, is more than the secondary carbocation with simple alkyl substituent, or you can say methyl groups. The third factor, two factors. First factor, substitution. The more the substitution, the more would be the stability of carbocation. Second is the pi electron in conjugation with carbocation. The conjugated pi electron stabilize the carbocation. The third factor is any atom bearing lone pair of electron adjacent to carbocation stabilize the carbocation. Now, come to some another examples. We have tertiary butyl carbocation on the left. Then we have secondary vinyl carbocation. In the end, we have alkyne carbocation. If you move from left to right, the left carbocation hybridization is sp3. You know, mostly it has been established that the carbocation hybridization in carbocation must be sp2, but in some cases like in SN2 reaction, the carbocation remains as sp3 hybridized. So sp3 hybridization, there is much crowding and there are more electron donating alkyl substituent that may stabilize the carbocation. But in second case, we have carbocation on sp2 hybridized carbon. Due to increased S character, the stability of this carbocation is lesser as compared to sp3 hybridized carbocation. In the end, the least stable carbocation is sp hybridized carbocation with, in case of alkyne carbon, terminal carbon here. So the hybridization factor also affect the stability of carbocation. The sp3 hybridized carbon is more stable as compared to sp hybridized carbon. Yes. Just it is for reference because we will discuss carboanion later in this course. So the same molecules of cation have been presented as anion in this sequence. The stability of anion is exactly reverse of that of carbocations. If we have carboanion means carbon with negatively charged electrons. So the carboanion in acetylene or any alkyne is more stable as compared to simple substituted alkane. It means the substitution in carboanion decrease the stability. Also the S character, decreasing S character also decrease the stability of carboanion. In summary, you can say the carboanion stability is exactly reverse of carbocation stability. As you can see, the sp3 hybridized structure of carbon, which is tetrahedral, sp2 trigonal, sp linear structure. Whereas the sp3 hybridized means one s and 3p orbitals combine to produce a degenerated same energy equal number of hybridized orbital. We have 4 orbitals here, 1s 3p, which combine together to produce same number of sp3 hybridized orbital. We will have 4 sp3 hybridized orbital like this. Similarly, for sp2, we will have 2 p orbitals with s that will produce planar structure, trigonal. Then sp, we will have linear structure. Now, come to next slide. In conclusion or summary, when you have mixture of different carbocations, then you can categorize them in order to arrange them in stability order. First, you have to look for aromatic carbocations. If any carbocation bearing aromatic character or any carbocation that is essential to have the aromatic character, they must be more stable among the rest. For example, in case of tropylium cation, as you have seen already in pKr plus determination, that tropylium ion is the most stable among all discussed cations in our previous lecture. This is the cycloheptane. This cycloheptane can have triene functional group here and positive charge here. This is termed as tropylium cation, 7-member triene cyclic structure. So this positive charge is in conjugation with other pi electrons, and we have ring current in this molecule. Therefore, the positive charge is essential for aromatic character of this molecule. Therefore, this carbocation is much more stable than any other carbocation. Then come to next category of carbocations with octet configuration. You know, carbocations are basically electron deficient, electrophilic nature molecules which always required a pair of electrons to complete its octet. When there is any lone pair pi electrons or sigma electrons which are in conjugation or in a position to support the stability of carbocation through provision of electron, then it would be better for its stability. Then next comes cyclopropyl group. Any carbocation bearing cyclopropyl can greatly influence the stability of carbocation through CC hyperconjugation. Then we can have benzyl carbocation in stability order, whereas allyls come next and alkyl carbocations come down in the sequence. From even simple methyl, the alkene olefinic carbocation that we also termed as vinyl carbocation is less stable, whereas phenyl carbocation is the least stable kind of carbocations. Now, after learning the factor responsible for the stability of carbocation, we can apply the concept in these examples. If you look at the first row here, we have 2-methyl-2-butene, which react with HCl to produce tertiary carbocation, whereas similar structure with absence of methyl group at position number 2, we have 2-butene that again reacts with hydrochloric acid to produce secondary carbocation. So the first reaction must be much more faster as compared to second reaction, because in first reaction we get stable carbocation as compared to second reaction. Similarly, in second row, you can see we have two different reactions. One is reaction of 1,3-butadiene with HCl to produce secondary carbocation with allylic conjugation. You see, allylic conjugation. Pi electrons are in conjugation with carbocation. There is stability factor. It means in second case we have one butene, only single pi bond at position number 1 and 2 between carbon 1 and 2. So that reacts with the hydrochloric acid to produce again secondary carbocation. Although we have secondary carbocation in both cases, but in first case we have carbocation in conjugation with pi electron. Therefore, first reaction must be faster as compared to second one. Now come to third example where we have same carbocation, that is isopropyl carbocation that reacts with two different reagents. In first case, it reacts with methoxybenzene, or you can say anisole, reacts with isopropyl cation to produce a secondary carbocation. You know, this is secondary carbocation attached with methoxy, because oxygen is not oxygen cannot termed as tertiary substituent to produce tertiary carbocation. Where in case of phenyl, reaction of benzene with isopropyl cation produce again secondary carbocation without any substituent. In first case, we have methoxy group that is providing electron, lone pair electron to stabilize carbocation, whereas in second case we don't have any stabilizing substituent with carbocation. So first reaction again must be more faster as compared to second. Similarly, we have another kind of reaction, reaction A and reaction B. In reaction A, there is 2-methyl-2-butene. Another is simple 2-butene. Though these two reactants react with hydrochloric acid to produce carbocation, in first case we have tertiary carbocation, whereas in second case we have secondary carbocation. Therefore, first reaction must be faster as compared to second reaction. I hope you must understand the stability order of carbocation when you face huge number of carbocation belonging to different composition. But within the same category, like all alkane hydrocarbons, alkyl substituents, then it is easily to arrange the carbocations. With increasing substitution, the stability increases, but the other factors may complicate the carbocation stability.